Hey everybody, Mr. Judson here. Hey, one quick thing. I need to have a mandatory meeting with all Central Washington students. I will send out an email, but this Thursday, I just need to get together with everybody, make sure that we're all on the same page, and so we will do that during office hours. So Thursday at 11 o'clock, we'll have a meeting. And I need everybody to be there. If for some reason you absolutely can't, get in contact with a friend and just make sure that somebody takes some good notes and can pass that information on to you. But I really would like to have everybody there, okay? All right, so we're talking about trig substitution. And so we can go ahead and push this idea just a little farther today, kind of more of the same. So why don't you guys go ahead and give this one a shot. All right, so let's see, we're adding two things together here. And so what I want to do is I want to let u equal a tangent theta. And so again, just establishing what u and a are, you got to say, well, what's being squared here? That's 2x squared. And so my u value is 2x. My a value would be 3. And so there's what I want to use for my trig substitution. So if I take the derivative of this, I would have 2, and I just took the derivative of x. Over here I would have 3, and the derivative of tangent is a secant squared of theta, times the derivative of the angle, which is 1, and I just took the derivative of theta. Again, real important to get that in there because we're going to need a d theta in the integral to be able to solve it. So if I go ahead and divide by 2, there's what I get. All right, so let's see. 2x, which is what's being squared here, is going to equal this. So what I want to do is I want to put in a 3 tangent theta and square that, plus 9, over... let's see, so x is going to equal 3/2 tangent theta. And I need to put that in here and raise that to the 4th. Oh my gosh. Alright, so 3/2 tangent theta, raise that to the 4th. Times 3/2 secant squared of theta d theta. Alright, so let's clean this up a little bit. Let's see, if I square this, I'm going to have 9 tangent squared. I'll go ahead and factor a 9 out of each of those. And so what I'm left with is tangent squared theta plus 1 over, if I raise this to the 4th power, I've got 3 to the 4th, I believe that's 81. 2 to the 4th, that's 16. And then we got tangent to the 4th of theta. And then here we still have 3/2 secant squared theta d theta. Integral of all that. I'm eventually going to move all these numbers to the outside. So let's see, the square root of 9 would be 3 times 3/2. I'm dividing by 81 over 16, so I'll flip it over and multiply. So that's all the numbers get moved to the outside. What I have left on the inside, this right here would be a secant squared. So if I take the square root of that, I have a secant of theta times a secant squared theta d theta all over tangent to the 4th of theta. Alright, so let's see, let's deal with these numbers here real quick. 3 times 3 is 9. If I divide this by 9, I would get 9. Divide both of these by 2 and get 8. And so what I have on the outside now is 8/9 times the integral of, let's see, I'm going to write this as tangent to the negative fourth power of theta times secant cubed of theta d theta. So this looks like one of those integrals we did in the previous section, where I would look at this and try and make sure I had the derivative. So let's see, the derivative of tangent is a secant squared. So if I pulled a secant squared out, could I change that remaining secant into a tangent? And the answer is no. If I see, the derivative of secant is a secant times a tangent. So if I kind of pulled that out, I would have a secant squared. This would be a tangent to the negative fifth. And can I convert tangent to the negative fifth into secants? No, I can't. So maybe I should go sines and cosines. Let's try that and see what happens. So I've got 8/9 times the integral of, so let's see, this would be 1 over the cosine to the third of theta. This tangent in the denominator, that would be sine to the fourth over cosine to the fourth. And what I have to do is flip that over and multiply. So I'd have cosine to the fourth theta over sine to the fourth theta, d theta. And so now what I get is 8/9 times the integral of, let's see, 3 of these would cancel with 3 of these, so I'd still have 1 there. And so now what I have is a sine to the negative 4 of theta times a cosine of theta d theta. And so now I look at this and say, well, this is something inside parentheses raised to an exponent. The derivative of a sine is a cosine, and so I could go ahead and just do substitution to finish that. So if I let u equal sine theta, then du would equal cosine theta times the derivative of the angle, which is 1, and I just took the derivative of theta. So I now have 8/9 times the integral of u to the negative 4 du. And so add 1 to the exponent, I get u to the negative third. Divide by negative 3, still multiplying by 8/9, and then plus c. So it looks like my answer, I've got a positive times a negative, so I'm going to get a negative answer here. Have a negative 8 over 27. Got to drop this u back down, make the exponent positive. And so that'll be sine to the third of theta plus c. Alright, so we still got to convert this back into x's. So if I go back to this right here, tangent theta, if I move that 3 over and divide, I get 2x over 3. And so then I'll draw my triangle. Here's theta. Tangent is opposite over adjacent, so that's 2x, that's 3. This will be the square root of this squared plus this squared. So 4x squared plus 9. That's what we had to begin with. And so what I want to do now is, I've got negative 8 over 27. And so I need to take the sine of theta and raise that to the third power. So sine theta would be opposite over hypotenuse. So that would be 2x over the square root of 4x squared plus 9. Raise that to the third. So I'm going to have to flip this thing over and multiply times a negative 8/27. So I'll cube each of these. So 2x cubed would be 8x cubed. And if I cube this, that would be 4x squared plus 9 raised to the 3/2. 1/2 for that square root. And then plus c. So those 8's would cancel. And so it looks like what I have is a negative 4x squared plus 9 raised to the 3/2 over 27x cubed plus c. And that is not what I got on my calculator. Alright, so I was a little baffled by why my answer didn't match the calculator. But what I did is I went and I graphed both of them. I graphed the calculator's answer and my answer. And what I got was, I don't know if you guys can see this, but what I got is two graphs that were exactly the same. So I think I did that right. This answer must be equivalent to whatever they got. So anyway, there it is. All right, let's try another one. All right, so we want to try and solve this integral, and right away I look at this and I think the derivative of this is 2x plus 2. I can make that happen, so this looks like a substitution problem. But what if they say you need to solve this using trig substitution? Then we have to do it, right? So let's see if we can solve this using trig substitution. It will involve, I'll just give you a slight hint, it will involve completing the square here. So it's probably where you want to start. All right, so if I start by completing the square, I would say I've got x squared plus 2x, put the plus 2 over here, and what I want to do is I want to take half of this and square it. So half of that would be 1, square it, you get 1. And if I just added 1, I need to subtract 1 over here. So now what I have is the integral of x plus 1 times the square root of x plus 1 squared plus 1 dx. Alright, so here's what's being squared. That's my u value. My a value is 1. So if u equals x plus 1 and a equals 1, I want to let u equal a, let's see, we're adding, so a tangent theta. So just 1 tangent theta. And so that means I have a tangent theta out here. Inside the square root, I've got a tangent theta squared plus 1. And I got to figure out what dx is. So the derivative of this would be 1. Just took the derivative of x. Derivative of 1 is 0. And the derivative of this is a secant squared of theta times the derivative of the angle, which is 1, and I just took the derivative of theta. So I want to put that in place of this dx. Secant squared theta d theta. Alright, so this would become a secant squared. So what I have is the integral of a tangent theta. Secant squared, the square root of that is a secant, times a secant squared, that would be a secant cubed of theta, d theta. And so now, let's see, this one works out a little bit better than the last one. If I do a secant squared of theta times a secant theta tangent theta, d theta, then if I did substitution, I would let u equal secant. The derivative of that is a secant times tangent. So I got everything I need. I'm not even going to put the u in because there's no additional numbers here. I'm just going to add 1 to the exponent and divide by the new exponent. So this will be a secant cubed of theta over 3 plus c. And so now all we got to do is convert that back to x's. So let's see, I need a picture of a triangle. Tangent theta is equal to x plus 1 over 1. So that'd be x plus 1 over 1, opposite over adjacent. So that means this will be the square root of that squared plus this squared, which is really this right here, which that is really equal to this right here. And so the secant, which would be the reciprocal of the cosine. So let's see, I'm going to call this 1/3 times. Cosine would be adjacent over hypotenuse, so I want hypotenuse over adjacent. So I'm going to say the square root of, instead of this, I'm going to write the original square root, x squared plus 2x plus 2. And I've got to raise that to the third power. And then plus c. So I think my final answer I would write this way. I've got x squared plus 2x plus 2 raised to the 3/2 plus c. There it is. And again, check that on the calculator. If for some reason you get something that looks a little different, graph this answer and the calculator answer, and if those two graphs are identical, then you know you got it right. All right, let's try one more. All right, let's go ahead and try this one. So I'm gonna think of this as the integral of e to the x times the square root of 1 minus e to the x squared dx, because when you raise an exponent to an exponent, you multiply those, which is what we're doing here. And so now I could say that my u value is e to the x, my a value is 1, and it looks like I'm doing a squared minus u squared, so that would be a sine. So I want to let u equal a, which is 1, sine theta. So that means I've got the integral of sine theta times the square root of 1 minus sine theta squared. And let's see, to figure out what dx is, I'm going to take the derivative of this, which would be e to the x, times the derivative of the exponent, which would be 1, and I just took the derivative of x, and that's going to equal a cosine theta, times the derivative of the angle, which is 1, and I just took the derivative of theta. And so that means that dx, I'm going to have to move this e to the x over here and divide, but e to the x is a sine, so this would be cosine theta over sine theta d theta. Does that make sense? E to the x is equal to a sine, so if I put a sine theta here, I got to move that over and divide. Okay, so I've got a cosine theta over sine theta d theta. And I chose not to write that as a cotangent because I saw that that sign would cancel with this sign. And so let's see, 1 minus a sine squared theta, that would be a cosine squared theta. Square root of that is a cosine, times a cosine. And so what I get is a cosine squared theta d theta. I think we did one of these yesterday. This is going to be one where once I go through and do my integration by parts, I'm going to end up with another cosine squared, and have to bring it back over to get a 2 cosine squared theta. So let's see, I got to just kind of work my way through that. So let's see, I believe the way I set this up yesterday was I said, let's let u equal a cosine theta, and dv is going to equal a cosine theta d theta. So take the derivative of this, and I get a negative sine theta times the derivative of the angle, which is 1, and I just took the derivative of theta. Here when I integrate, I get v equals a sine theta. So I want u times v, so that would be sine theta cosine theta minus the integral of v du. So let's see, v du, when I multiply these I get a negative. Sine squared theta d theta. And so I'm trying to solve for a cosine squared of theta d theta. So I need to somehow see a cosine squared over here. So I'm going to change this using the Pythagorean identity to 1 minus a cosine squared. So the integral of cosine squared theta d theta is going to equal sine theta cosine theta plus the integral of 1 minus cosine squared theta d theta. And so what I'm going to do is I'm going to go ahead and make this into two separate integrals. There's one, there's the other. So when I bring this over here and add it to this one, I would get two of those. I still have sine theta cosine theta plus the integral of 1 d theta, which is just theta, plus c. And so now if I get that integral of cosine squared by itself, by dividing by 2, that's what I was trying to solve for. So I'll just get rid of this and say I've got that divided by 2 and that divided by 2. Constant divided by 2 is still a constant. And so now we just need to convert back to x's. So let's see. Sine theta is equal to e to the x over 1. So I'm going to make my triangle here. Here's theta. I know sine is opposite over hypotenuse, so e to the x over 1. So this has to be the square root of the hypotenuse squared minus this squared. E to the x times e to the x is e to the 2x. And so now we can start putting that stuff back in. So let's see, I've got 1/2. Sine of theta is just e to the x. Cosine theta is adjacent over hypotenuse, 1 minus e to the 2x, plus 1/2 times, let's see, theta is going to be the arc sine of e to the x. So, boy, I can't fit that up there. Sine to the -1 of e to the x plus c. So let's see, here's my final answer. I got to find some place to write this. I've got 1/2 e to the x root 1 minus e to the 2x plus 1/2 arc sine e to the x plus c. Oh my gosh. These are getting a little messy, aren't they? I don't ever want to say never, but it's not very often you see something this difficult on the Central Washington test. If you can get through this, you're good to go for that final. All right, that's what we have for today. Let me get you guys an assignment. All right, so here's what we got. Assignment number C16. We're on page 549, 23 to 35 odd. So don't forget, our final exam, I think I said in the last video, is going to be June 9th. And also we have a mandatory Central Washington meeting this Thursday. I need everybody to be there. Okay? All right. That is it. Talk to you guys tomorrow. Memorial Day weekend coming up. All right, take care.